Good morning, dear students. In the earlier class, you have learned the terms physical quantity and different types of physical quantities. Yes, we define physical quantity as any quantity that can be measured is called as a physical quantity. And these physical quantities are differentiated into two types: fundamental or base physical quantities and derived physical quantities. And we also have other type, they are supplementary physical quantities. Yeah, when we see fundamental or base physical quantities, so we have 7 fundamental physical quantities. So fundamental means they are basic quantities itself. They do not depend on other physical quantities. The 7 base or fundamental physical quantities are, you have already learned: length, mass, time, electric current, thermodynamic temperature, amount of substance, and luminous intensity. And we also discussed supplementary physical quantities. So we have two types of supplementary physical quantities, that is plane angle and solid angle. Yes, so I'll tell you why the plane angle and solid angle are called supplementary physical quantities. Yes, plane angle, how are we defining plane angle? Theta is equal to S by R. So if we are taking like this, we are taking an arc, this is the arc, this is the center of the circle, this is R, and this is the arc length. And when we see, suppose when you take this, S is equal to 2 meters and R equal to 1 meter. So what do we get? Theta is equal to S by R, 2 meters divided by 1 meters. So meter gets cancelled, right? So what do we get here? We get 2. 2 is a number, right? So do we get any units here? Do we get any unit here? No, we don't get any unit actually, because meter gets cancelled, isn't it? Actually, it is unitless quantity, but we are assigning a unit to understand that this theta is a plane angle. Suppose if I say x is equal to 2, it doesn't make any sense. But if I say x equal to 2 meters, that means x is a distance or displacement. So we understand like that. In the similar manner, if we say theta is equal to, if I say theta is equal to, it doesn't make any sense. We cannot understand. But that is the reason why we assign a unit to this plane angle. So what is that unit? Radian. We call it as radian. Isn't it? Do you understand? Actually, it is unitless, but to understand, so we are assigning a unit that is radian. So when we say radian, it is a plane angle. In the similar manner, phi. So when you take solid angle, yeah, we take certain curved area here, and we say this is area A and this is R. So how do we define A by R square? Suppose let's say this area is 4 meters square, and let's say this radius is 1 meter. Radius R equal to 1 meter. So 1 meter R square, 1 meter whole square, right? That means what do you get? 1 meter square. So meter square gets cancelled. So phi is equal to, what do we get? We get a number 4. We get a number 4. So when we say phi is equal to 4, does it make any sense? No. That is the reason why. So this solid angle is also unitless. But to understand it is solid angle, we assign a unit. So which is called as steradian. We call it as steradian. So actually plane angle and solid angle, we get only numbers. But to understand it is plane angle, we call it as radian. To understand this solid angle, we call it as steradian. That is the reason why these two are not considered as base physical quantities or derived physical quantity, because they are actually unitless. So we are assigning unit to plane angle and solid angle. That is the reason why they are called as supplementary physical quantities. Yes, in the earlier class I explained you what is unit. What is unit? A unit is a standard reference. So to measure any physical quantity, we need a standard reference of the same physical quantity. The standard reference is called unit of the physical quantity. Suppose if you want to measure mass, so first we need to have a standard reference, right? So we take 1 kg as a standard reference, isn't it? Yes. So scientists took an alloy, I think it is made up of some material, and they took certain amount of mass and they said that is 1 kg. So they took 1 kg like that, and in 1 meter also. So the standard units are usually chosen arbitrarily. So they took certain amount of mass and they said 1 kg, isn't it? When it comes to length also, they took certain amount of length and they said 1 meter. And in the similar manner, time also we know. What is the unit of time? Second. So that means to measure any physical quantity, we need to have a standard reference. The standard reference is called unit of that physical quantity. Now let us write the definition here. Yes, so this is the definition of unit. To measure any physical quantity, we need a standard reference of the same physical quantity. The standard reference is called the unit of the physical quantity. When we take kg, scientists took a cylinder which is made up of platinum iridium and they said that is 1 kg. So when we compare to, now we want to know mass of some object. So the second object. So if the mass of the second object is 2 times of that cylinder, we say that the second object has mass 2 kg and so on. So that is the standard one we are taking, internationally accepted 1 kg. So compared to that one, if other object is 10 times, we say the second object has mass 10 kg and so on. Now let us see various system of units. Yes, so these are the types of system of units we have. CGS system, CGS unit system, FPS unit system, MKS unit system, SI unit system. When we take the first three fundamental physical quantities, length, mass, time. In CGS system, the units are, the unit of length is centimeter, the unit of mass is grams, the unit of time is second. CGS, centimeter, gram, second. FPS, this system is also called as British system. Foot, or we can also say feet. Foot or feet, pound, second. FPS, foot, pound, second. This is also called British system. And the next one is MKS, meter, kilogram, second. M stands for meter, K stands for kilogram, S stands for second, isn't it? Yes. But usually we do not, the internationally accepted one is SI only. Yes, SI stands for System International Units. In French, System International Units means International System of Units. In English, International System of Units, but in French, System International Units. So this is SI system is accepted throughout the world, but not these three. And most of the SI system units are taken from MKS. Most, not all the units. So most of the units are taken. Most of the SI units are taken from MKS system only. And for meter and kilogram, second, we have definitions in our textbook, but it's better not to remember, because meter means certain length, it is called as meter. Kilogram means it is a standard mass, certain amount of mass, and it is called kilogram. Second means a small duration of time, it is second. That's it. It's better to remember like that. But we also have standard definition for meter, kilogram, and second. So it's better not to memorize it, because it's very difficult to remember, and usually they are not asked in the exam. Yes, now let us see other types of physical quantity, that is derived physical quantity. A physical quantity that can be expressed in terms of fundamental physical quantities is called derived physical quantities or quantity. Yes, now let us see few derived physical quantity. Yes, so we have many derived physical quantities. Just here we are writing 10. Yeah, area. As I have told you again, well, let us take this example, this matchbox. Now you want to find this area, this side. So what do we need to do, guys? So this length into this length, we get area, right? That means, so area depends on length, isn't it? It can be expressed in terms of this length and this length. That's why area is called as a derived physical quantity. But what about the length? Length, is it derived physical quantity? No, it's a fundamental one. From length, we can, from any other physical quantity can be expressed in terms of length, but length cannot be expressed in terms of other physical quantities. So area, length into length. So what do we get, guys? Meter into meter, we get meter square. So here units we let us write, and this is again SI units. Area, what is the unit of area? Meter square, because suppose if this is 5 meters and this is 4 meters. 5 into 4, 5 4s are 20, and meter into meter, meter square. So 20 meter square is the area of this surface. And volume. How do you find volume? If it is a cuboid, what do we need to do, guys? This length into this length into this length. LBH. So this is in terms of meter, this is in terms of meter, and this is in terms of meters. So meters. Meters into meters into meters. What do we get? Meter cube. So what is the unit of volume? Meter cube. And volume is expressed in terms of length. How many lengths we have? 3 lengths. And here 2 lengths. So do you understand why area and volume are called derived physical quantity, because they are derived or they are expressed in terms of length. And when it comes to velocity, so how do we define velocity? Displacement divided by time taken. So displacement, what is the unit of displacement? Meters. And what is the unit of time? Seconds. So velocity means, what is the unit of velocity? Meter per second. Displacement divided by time. So velocity is expressed in terms of which quantity? Length and time. So velocity is a physical quantity, but it depends on which quantity? Length and time. So that is the reason why velocity is a derived physical quantity, and so on. So like this, if you see all these physical quantities, they are expressed in terms of fundamental, few or some of the they are expressed in terms of few fundamental physical quantities. And acceleration, how do we define acceleration? Change in velocity divided by time taken. Change in velocity means meter per second by time taken, again second, that means meter per second. That means we can write meter per second square, meter per second square. This is the unit of acceleration. And density, how do we find density? It is the ratio of mass and volume, mass divided by volume. For mass, what is the unit we have? Kilogram, kg. Mass divided by volume, volume means, what is the unit of volume? Just now here we have written meter cube, kg per meter cube. This is the SI unit of density. And force, how do we define force? It is the product of mass and acceleration. Mass and acceleration. What is the unit of mass? Kg. And what is the unit of acceleration? Meter per second square. Meter per second square. So kg meter per second square. This is also called as Newton. This is also called as Newton. And we use capital N. Remember, whenever any unit is used on the name of any scientist, we are supposed to use capital letter. So Newton is a scientist. That's why for force we don't write small n, we write capital N. If you see the fundamental physical quantity, that is electric current. For electric, what is the unit of electric current? Ampere. But Ampere is also a scientist. That is the reason why there we use capital A, not small a. We always use capital A. So whenever unit is used on the name of any scientist, we are supposed to use capital letter. And work, how do we define work? It is the product of force and displacement. Force and displacement. Force means, already what is the unit we have? Kg meter per second square. This is the force, and to displacement. Displacement means meters. That means we need to multiply this quantity with m. So what is the unit we get? Kg meter square per second square. Instead of writing this whole thing, we write joule. Joule is again a scientist name. That's why we use capital J. Instead of writing this whole thing, you can also call it as joule J. And impulse. And impulse, the product of force and time duration is defined as impulse. Yeah, here Newton into second. You can write Newton into second. And momentum, the product of mass and velocity is defined as momentum. So for mass, what is the unit we have? Kg. For velocity we have meter per second. So kg meter per second, this is the unit of momentum. And power, how do you define power? The rate of work done. Work done divided by time taken is defined as power. Of course, for power you can write directly joule per second, or joule per second means, yeah, for work we have this quantity, right? So this whole quantity divided by time you can write, or simply for power, already this joule we have this quantity. So joule per second, or this joule per second is also called as watt. Again we use capital W. What is the scientist name? That's why we use capital W. So here we are writing only 10 quantities, but we have many physical quantities, isn't it? Yes. Limitless. We have limitless derived physical quantities we have. But when it comes to fundamental or base physical quantities, how many we have? We have only 7 fundamental physical quantities and 2 supplementary physical quantities. But what about derived physical quantities? Can we give any number? No. We cannot give a particular number to derived physical quantities. We have many derived physical quantities. Now let us try to understand what is dimension. Yeah, later you will discuss dimension analysis. First, let us try to understand what is dimension. In space, if we want to represent a point, so how many dimensions does it have? Yeah, in space, usually to represent a point, what do we do, guys? We take like this. We take x-axis, y-axis, and z-axis. Of course, this z-axis is perpendicular to the plane like this. Here z-axis, how is the z-axis? Perpendicular to the plane like this. Now here in the space, if I want to represent any point, so how many values we give, how many dimensions does it have? So in x direction it has some value, in y direction it has some value, in z direction it has some value. That means in space, not on the xy plane, I am showing a point here, but of course I am writing on this plane, but let's say this point is in the space here, in the air. Now I represent this point like this, 3, 4, 5. So what is it in, guys? What is the x dimension value? 3 meters. What is the y dimensional value? 4 meters. What is the z dimensional value? 5 meters. That means in the x direction, so what is the distance it has? It is from origin to here, it is at 3 meters. In y direction, so what is the distance it has from origin? 4 meters. In z direction means perpendicular to the paper plane, in the air here at somewhere, from the plane of the paper to here. So what is that value? 5 meters. So that means, so totally how many dimensions we have? So maximum dimensions to space we can give only 3. Of course we also have 4th dimension, that is time, that you will be learning in higher classes. But as of now, if we take only space, so how many dimensions can we give to any point? 3 dimensions, right? Maximum dimensions are only 3 dimensions. Yes or no? But in physics, if we take any physical quantity, it can be expressed in terms of fundamental physical quantities, right? So that's why what we do is we assign dimension to first fundamental physical quantities. We assign one dimension to every fundamental or base physical quantities. Now I'll explain. First, let us assign a dimension to fundamental physical quantities or base physical quantities. Yes, so if you see the base physical quantities, so we have 7 base or fundamental, whatever you call, both are same. 7 base physical quantities we have, and units, we have units of the same 7 base physical quantities and the symbols which we use. Units, and this is SI units only. Now let us assign dimensions, dimension formula, dimension to each physical quantity, each base physical quantity. So for length we assign, for length what is the starting letter? L. We say L. And the dimension formula or the dimension formula for length is L. The dimensional formula for mass is M. For the dimensional formula for time is T. The dimensional formula for electric current is, in some books we use A, in some books we also use I. Thermodynamic temperature. For thermodynamic temperature, remember, Kelvin, unit is the Kelvin and symbol is capital K. Again, for ampere we are using capital A, for Kelvin we use capital K, because Kelvin is also a scientist's name. That's why temperature we are not supposed to write small k, it must be capital K. And the dimensional formula for temperature is also capital K. For amount of substance, the dimensional formula is MOL, and the dimensional formula for luminous intensity is CD. Just now I explained you. So in 3-dimensional space, so how many dimensions can a point have? Only 3 dimensions. In the similar manner, that means if we take a point in the space, so we assign only 3 values: x value, y value and z value, because every point can be represented with only x, y, z values. In the similar manner, in physics, if we take any physical quantity, that can be expressed only these 7 fundamental physical quantities. And for every physical quantity we are assigning a dimensional formula. That means, so if we see any other physical quantity, so when we write dimensions of any other physical quantity, so maximum dimensions of that derived physical quantity, so how many? Only 7. So the dimensional formula, the dimensions of any physical quantity, any derived physical quantity, if we see, so it may have length, mass, time, this A, K, MOL, mole, candela. Only it can have only these 7 dimensions. So we can say the physical world has how many dimensions? 7 dimensions. The physical world or the physical quantities have how many dimensions? Maximum dimensions? 7 dimensions. Yes, I am comparing the 3-dimensional space to this physical quantities, because in 3 dimensions we can give only 3 values, right? That is x coordinate value, y coordinate value and z coordinate value. We can give only 3 values and we say 3 dimensions. But in physics, if we take physical quantities, so if we take any physical quantities, it can be expressed some or few of these 7 fundamental physical quantities. When we write dimensional formula for any derived physical quantity, so we will get these few. Usually we do not get all this. We may get LM, we may get MT, and so on. Now let us see few derived physical. Let us see the dimensional formula for few derived physical quantities. Yes. Now let us see the dimensional formula for a few derived physical quantities. So the first derived physical quantity we are taking area. Area means the unit is meter square. But how many lengths we have? Area means length into breadth. Of course, breadth is also length, right? So L into L. So what do we get, guys? L square. So the dimension formula for area is L into L. That is L square we can write. And the volume. For volume, how do we get volume? Length into LBH. Length into breadth into height. But that may be length or breadth or height. So each one is length, right? Length into length into length. So how many lengths we have? 3 lengths. So we write L to the power of how much? 3. And when we take velocity, displacement divided by time taken. For displacement, what is a dimension? Length by time taken, time. L by T. So L by T, we can write L T power minus 1. L. So this is the dimensional formula for velocity. Acceleration, the change in velocity divided by time taken. So change in, for velocity, what is the dimensional formula we have? L T power minus 1. So change in for velocity or change in velocity, both have same units and same dimensions, right? So change in velocity divided by time taken. So this is the change in velocity divided by time taken. So L T power minus 1 by T. So what do we get? L T power minus 2. This is the dimensional formula for acceleration. So how are we getting acceleration dimensional formula? From velocity only. For velocity or change in velocity, the dimensional formula is L T power minus 1 by time taken T. So we get L T power minus 2. And density. For density, what is the dimension formula we have? Mass by volume. For mass, what is the dimension we have? M by volume. Volume means we have L cube. So M by L cube. So instead of writing M by L cube, we write M L power minus 3. So this is the dimensional formula for density. For force, what is the dimension? What is the we have? Mass into acceleration. For acceleration, what is the dimension we have? L T power minus 2. But for mass, what is the dimension we have? M. So for force, first kg means we are not supposed to write kg here. For kg, what is the dimension formula we have? Mass. That is M meter per second square. That is acceleration. So L T power minus 2. So this is the dimensional formula for force. Now when we see impulse, how do we write? Newton to second, right? Newton to second means kg meter per second square into second. So we are getting kg meter second. Kg means mass. We get M, and from M means length. L by time, second. So M L T power minus 1. So this is the dimensional formula for impulse. When we write units, you can write anything. Newton second or kg meter per second, both are right. But when you write dimensional formula, this is the correct dimensional formula for impulse. And work. When we see work, how do we write work? It is the product of force and displacement. So for force, already we have ml T power minus 2. And so force into displacement. So multiply this value with displacement. Displacement in length, right? So already L power, how much is there? 1 is there. So if we multiply with L, what do we get? L power 2. So for work, what is the dimensional formula we have? M L T power minus 2, but into length, right? So M L power 2 T power minus 2. This is the dimensional formula for work. And momentum. So for momentum, what is it? Kg meter per second square. Kg meter per second. Mass into velocity. So for kg means mass, we have M L T power minus 1. So this is the dimensional formula for momentum. If you see impulse and momentum, these two have same dimensions. You will come to know why these two have same dimensions in the upcoming classes. So impulse and momentum, these two have same dimensions. In fact, they also have same units also. But here we are representing in different units, Newton second and kg meter per second. But in fact, these two units are also same. And power. How do we define power? That is work divided by time taken. Work divided by time taken. Joule per second. So kg meter per second square by second. So what do we get? Kg meter square per second cube. So for kg means mass. For meter square means L power 2 second. That means time. So T power how much is there? T power minus 3 is there. Now do you understand? So in space, if we take any point, so we can assign only 3 values, x, y, z values, isn't it? But when it comes to physical quantities, isn't it? Yes. So the dimensions of if we take area, the dimension of L is how much? 2. And when we take volume, what is the dimension of L? 3. And usually most of the physical quantities can be expressed in terms of MLT only, mass, length, time. So that's why instead of writing L power 2, we also write m power 0, and we also write t power 0. If m and t are not present, usually we write it as m power 0 and t power 0. Here also we can write m power 0, t power 0. And here m is not present, so m power something to the power of 0, how much? We get 1, right? So that's why here you can write, usually we write like this. So why we are introducing m and t here? So most of the physical quantities can be expressed in terms of mass, length and time. The dimensions of most of the physical quantities depend on mass, length, time. And here mass is not present, you can write m power 0, and here ml present but t is not present, you can write t power 0. Here 3 are present, here 3 are present, here 3 are present. So here you need not to write anything. But if ml in mlt, if one of these 3 is not present, you can write that that dimension power 0. Now when we take power, what is the dimensions of power? Isn't it? Yes. So the dimension of power, m power is how much? 1. So mass dimension is how much? 1. And length dimension 2, and time dimension minus 3. Now do you understand what is dimension? So in space we can assign only 3 values, x dimension, y dimension, z dimension to a point in the space. In the similar manner, in physics, if we take any derived physical quantity, so it can be expressed in terms of fundamental physical. We are writing first, we are assigning dimension to fundamental physical quantity here. Now what is the mass dimension in power 1? What is the length dimension in power 2? What is the time dimension in power minus 3, and so on. So just we are writing only 10 here, but we have time t power m, L power 2, t power minus 3. So if we take any physical quantity, any derived physical quantity, we can write like this. We can write dimensional formulas like this. And the use of dimensions is, we can check the consistency of an equation. If an equation is given, we can check whether the given equation is correct or not. Now I'll tell you, let us take an example for this one. Yes, checking consistency of an equation using dimensions. Now we have equations of motion. A simple equation I am taking. S is equal to ut plus of at square. Now let us check the dimensions of S. What is the dimension of S, guys? S means displacement, right? So what is the dimension of S? We get length, right? So we get L. Now let us take the dimensions of ut. This side ut. Let us take individually u and t. U means, what is u here? Initial velocity, right? So what is the dimension of initial velocity? Velocity L t power minus 1. And what is the unit of time? What is the dimensional formula for t? Time. T power 1 is there, t power minus 1 is there. So what is the dimension of this quantity? Ut. We get L. Now of at square. Now check the dimension of at square. For half, it's a constant, right? Does it have any dimension? It's a pure number. So take this side, dimension of a and dimensions of t square. What is the dimension of a? Acceleration. So we have only learned L power t power L into t power minus 2 is there. And what is the dimension of t? T. So t power how much is there? T power 2 is there. T power 2. T power 2, t power minus 2. So what do we get? L. So that means, so here the dimension of S is L, the dimension of this quantity is L, and the dimension of this quantity is also L. That means, so LHS is equal to, we are getting RHS. So that means this equation is correct. So in LHS and in RHS, we should get same dimensions, then only the given equation is correct. If we get different dimensions in left hand side and right hand side, we can say that the given equation is wrong. So this is the way we can check whether the given equation is right or wrong using dimensions. And remember guys, not only dimensions, you can also check the units. When we write units, if I write 10 meters is equal to, I can write 8 meters plus 2 meters. If we write like this, is it correct? But 10 meters is equal to 8 meters plus 2 seconds. Does it make any sense? No, isn't it? When you add or subtract, the quantities must be same. The units must be same. We cannot add, that means 8 meters plus 6 meters. So what do we get, guys? You will get 14 meters, right? Or 8 meters minus 6 meters. So what do you get? You get 2 meters. But 8 meters plus 6 seconds. Do you get anything? No, it doesn't make any sense. 8 meters minus 6 seconds. Do you get anything? No. So it doesn't make any sense. So when you add or subtract, what do? The same quantities can only be added and the same quantity can only be subtracted from one quantity to other. But when it comes to multiply and division, you can you can multiply different quantities and you can divide different quantities. But for addition, subtraction only, the quantities must be same. Yeah, this is about today's class, and in the next class, yeah, we'll discuss prefix of units and measurement of length and range of lengths and so on.